Yeah, do you guys remember SA1? It's also JA3.
Oh yeah. And then SA3 was also JA5.
Yeah. So the question was like, if you have n, 2n, 3n, all the way up to 9n, yeah? What is the minimum number of distinct leading digits you can have, yeah? And you're told that they're all positive integers, yeah? Okay, and n is not 0. Yeah, so I think it's one of those things, the problem itself is not very hard to solve. It's the proof that's a little bit hard to write, you know? So we used to never really address that so much, but this is maybe a perfect opportunity. So one thing, so obviously you could start with an example, and there's not really any way around that. For example, n equals 25, you know? You see that there's this 4. You just write out the numbers. Right, and you see that there's four leading digits, you know? So this is 1, 1, 1, and then 2 is there, right? So I guess with the proof, it's usually like it's usually opposite to how you solve it, you know? Because when you solve it, you get to the answer at the end. In the proof, you kind of, it's like you don't care about spoilers or punchlines. You just tell people the answer at the start, yeah? So you want to say like this is 4, yeah? And then you proceed to prove it, yeah? So this example proves that it's less than or equal to 4, yeah?
Yeah.
So now you want to prove that it's not 1, 2, or 3, yeah? There's a lot of ways you can organize it, but there's one cool idea that makes the write-up kind of nice. So you can write this as like a note or a lemma, but basically, so if you have n is greater than 10 to the k is less than 10 to the k plus 1 for some k greater than 0, yeah? So it's saying that n has k plus 1 digits.
Yeah, and that's k.
Yeah, and then n plus 10 to the k, yeah? So assume this is also less than 10 to the k plus 1, you know? Okay. Then m plus 10 to the k, or maybe another way of saying it, so m m plus 10 to the k has a larger leading digit, yeah? So it's kind of obvious, but it's really just stating something that puts this into the foreground. So basically what 10 to the k is the value of the first digit, right?
Yeah, minimum value for n.
Yeah, so like you're basically just adding 1 to the first digit of n, right? So the digit has to increase if it doesn't carry, you know?
Yeah.
So it's a really trivial lemma, but when you think of it this way, it actually makes a lot of it very easy to prove. So the proof is, see the very first one is always the, maybe, so Yeah, I guess it essentially means that n has leading digit 8 or something. Yeah. But like you could almost, depending on what the context is, get away with saying this is obvious. Yeah. Okay. Then now you look at something like Okay, so now we have now consider k is in naturals the least integer such that maybe not k, maybe l, yeah. So we fix n is greater than 10 to the k is less than 10 to the k plus 1, yeah. Consider l is the least integer such that n, 2n, 3n up to l minus 1n is less than 10 to the k plus 1, yeah, and ln is greater than or equal to 10 to the k plus 1, yeah. So you could actually have said, you could actually skip this part is actually not, you don't actually need to even state that part, yeah. So it being the least integer that ln is greater than or equal to 10 to the k plus 1 already means that, but that's sort of an explanation of what, yeah.
You can also say the largest integer and then don't write ln. So like to ln l minus 1 is less than 10 to k
Oh
plus
yeah,
1.
you can make L the largest that stays under, yeah.
Yeah.
Okay, but in either case, so this gives you a bunch of cases, right? So you have the case that, yeah, or if you want to make the L the largest. Okay, how about that? Such that ln is less than 10 to the k plus 1, yeah? So this gives you some cases. So L could be greater than or equal to 4. L could be equal to 3. L could be equal to 2. And L can't really be 1, right?
Well, it can.
Okay, okay, L equals 1, okay. So let's just examine these cases in turn, yeah? Okay, so if L is greater than 4, right?
Well, we're looking for L is three or less. So like the number of digits is 3 or less. So we don't really need to look at L is greater or equal to 4. Because that
Yeah.
implies that there is already 4 digits at least.
Yeah, exactly. And I think I'm trying to prove it, okay? So if L is,
using the lemma, yeah.
yeah, so if you use the lemma, you get, so for example, you take I is greater than 1 is less than L, you know? And you see that I plus 1 times n, you know, is equal to in plus n, okay? And this is greater than or equal to in plus 10 to the k, right? And this is also less than 10 to the k plus 1, yeah? So you can see that proves it has more digits. It has a bigger leading digit, yeah? So therefore, in plus 1 n has larger leading digits. You can even state this is a lemma, I guess, than in, you know? So that gives you, so by 1, yeah? So that gives you, maybe you can call this lemma 2. Okay. So 4 is just by lemma 2, there's at least 4, yeah? Okay, so but when you have 3, you have lemma 2 gives you, so we can even come up with like a notation, like we could say like, this will maybe like save a lot of writing. So we could say n triangle m, you know what I mean? Or p triangle q.
Right.
If p has, how about n, capital N, yeah?
Yeah.
If n has smaller leading digit than n, right? And we get, so from 2, so here then you can write this as n 2n 4n, right? And here you have n 2n 3n, right?
Yeah.
Okay, and then you have the 4n. It says, but now the 4n, right, is bigger than or equal to. Okay, so the 4n isn't on this chain anymore, right? That's the difference. Okay. Okay, and I want to prove that actually 4n is below the chain. You know? Okay. So how would you prove this? Well, so for 4n to get over the outside the chain, it has to be bigger than or equal to 10 to the k plus 1, right? Okay. So if 4n is bigger than 10 to the k plus 1, then 6n, so 4n is less than 6n, right?
Yeah.
Less than or strictly less than 6n, which is less than or equal to 10n minus 4n, right? Well, this is equal to, and that's less than or equal to 10n minus 10 to the k plus 1, right? Yeah?
Yeah.
So can you see that proves that it actually has one less digit than n, because 10n is the same leading digit as n.
Yeah.
You know? So it's all kind of obvious, but when you write it, it's kind of, it's like another, it's almost like something else. Maybe this is how the AIs would do it. Okay, so maybe to phrase it in terms of our lemma. So you get 10n is greater than or equal to, wait, it's greater than or equal to 4n plus 10 to the k plus 1, right? And is less than 10 to the k plus 2, yeah? So by 1, 10n is greater than 4n, yeah? No. But 10n, we maybe have another notation, equals n, yeah?
Oh, more 10.
like
More the last digit. More the triangle.
Yeah, so I guess it'd have like this, we'd have both.
More triangle.
So 4n is triangle n, right? It's almost too clean, you know what I mean? It's kind of, it's almost like people forget that you're just timesing numbers by 5. Okay, so now you have L equals 2, right? So L is equal to 2, you have N is triangle 2N, right? But then you have 3N is bigger than or equal to 10 to the K plus 1. Okay, so then you have 7N is you have 7N is less than 10N minus 10 to the K plus 1, right? So that shows that 7N is smaller than N, right? Yeah. So that also shows, so if you do it again, you get 4N is smaller than 7N, right? So, so for example, now you have 4N is smaller than 7N is smaller than N is smaller than 2N, right?
Yeah.
Yeah, I found once you got the right notation, it's kind of exponential. It's kind of pretty crazy. Okay, L equals 1 is trivial, probably. So N, the 2N is greater than or equal to 10 to the K plus 1, right?
Yeah.
So then you get 8N is smaller than N, which is bigger than 6N, it's bigger than 4N, it's bigger than 2N, yeah? So you can even prove it has at least 6, yeah? Alright, I will repeat some of this for you. So basically today is an awkward mix of egg mode day 1, some sort of mix making up for the Friday anomaly.
Friday anomaly?
Yeah, and me trying to complete some topic. A lot of people aren't coming Friday because of Easter.
Oh yeah, Easter.
Okay, let's see if we can write this up again, you know? Okay. So, notation.
Yeah. Triangle.
Notation. Oh, wait, you don't even know what we're doing. Okay. So, the question we're doing is, you remember JA3?
Yeah.
It's like N, 2N,
2 and 3.
Yeah.
9N. What is the min number of leading digits, yeah? So we're trying to write the perfect proof. Okay. So the min number of leading digits we claim is 4, yeah? So you claimed that at the start. Claim 4, yeah? Okay. And then you can start with an example, n equals 25, yeah? And that'll show it's less than or equal to 4, yeah? Okay. Come up with some notation. We say, let's think of some letters here.
N and capital
Or
N.
I, no. I is less than J, yeah? If leading digit of I less than leading digit of J, yeah? And maybe you could say I square J if both I is less than J and J is less than I, yeah?
Okay.
Clearly.
Less than. Is it leading digit?
Yeah, it's the triangle means clearly like I less than J less than
Yeah. How can the
K.
leading digit of I be less than J and the leading digit of J be less than I?
Less than.
Oh
Yeah,
crap,
less
okay.
than equal to.
Okay, sorry, if they're equal, yeah.
Yeah.
Let's not make it less than or equal to, let's just say strictly less than, yeah? I heard this, I is congruent to J if same, yeah?
Oh yeah.
Okay. It looks like we're working hard, but this saves a lot of work.
Yeah.
Yeah, so you can start with like a lemma, yeah? So start with 1, If so, maybe before you start with 1, you just let so fix kind of n to be between 10 to the k and 10 to the k plus 1, you know? And then you can say if n plus 10 actually maybe that could be part of the lemma, but n plus 10 to the k is less than 10 to the k plus 1, then maybe it looks nicer if you write it like this. If it's less than or equal to m, which is less than 10 to the k plus 1, then n is m. Yeah? Yang? This is predominantly for you. Okay? So I guess proof. Yeah, so maybe proof is. This is awkward still. How do we make it nicer? Adding 10 to the k increases leading digit by 1 since m plus 10 to the k is less than 10 to the k plus 1. M, there is no carryover. To decrease leading digit. Okay, now let L be largest integer less than 9. Oh, I guess it doesn't have to be less than 9, but such that n to n ln is less than 10 to the k plus 1. Yeah. Okay. So this gives us immediately cases, right? L is greater than 4, L equals 3, L equals 2, L equals 1. So if L is greater than or equal to 4, okay, we're gonna have a lemma right here, okay? That the conclusion is n is less than 2n is less than ln, yeah? And the proof is just if you take I is greater than 1 less than L, I plus 1 n is less than it's less than or equal less than L less than or equal to Ln, right? Which is less than 10 to the k plus 1, and it's equal to In plus n, which is bigger than or equal to In plus 10 to the k, right?
Yep.
Okay, so therefore by 1, we're done. Okay, so then for L is greater than or equal to 4, we have from 2 that n is less than 2n, is less than 3n, less than 4n. Yeah. Okay. L is equal to 3, we have from 2 that n is less than 2n, less than 3n, and we have that 4n is greater than or equal to 10 to the k plus 1, right? So therefore, we have that 6n equals 10n minus 4n is less than or equal to 10n minus 10 to the k plus 1.
Yeah.
Okay. And so basically you have 10n is greater than or equal to 6n plus 10 to the k plus 1. Yeah? So therefore by 1, 6n is less than 10n, which is equal to n, right? So therefore 6n. Yeah, you could try harder to see exactly how many there are, but at the moment we're just writing. So in research, the next natural question is like, which n give you which numbers of digits? Okay. Then when L equals 2, we have n is less than 2n, right? And then 3n is greater than or equal to 10 to the k plus 1. So that means 7n is equal to 10n, greater than or equal to 10n minus 10 to the k plus 1. Yeah?
Yeah.
Because 3n is bigger than that, you're minusing 3n. So that means 10n. It's the same with so 10n is bigger, less than, wait, I have the wrong direction. 7n is smaller than, right?
Yeah.
So 10n is bigger than or equal to 7n plus 10 to the k plus 1. So therefore 7n is less than 10n, which is equal to n, right? Yeah, so similarly, oh, it's Leo. So 4n is less than 7n, right? You got 4n less than 7n is less than less than n, which is less than 2n, right?
Yeah.
There's at least 4. And then for L equals 1, we have 2n is greater than 10 to the k 1. So you get 8n is less than n is less than 6n is less than 4n is less than 2n. Yeah? Yeah. So I guess it's quite fast.
Yeah.
Okay, when Leo gets here, I will repeat it again. Maybe it'll be faster somehow. We're just gonna get that first step. Get that first step.
Explain how lemma one works again.
Yeah, lemma 1 works. Yeah, that's really the thing Maybe I'll explain it when Leo gets here, because then lemma 1 is the key behind all this, yeah. Leo, welcome. So maybe we can do EGMO day 1. You want to do it times, you might have to sacrifice just the second 2 questions then.
Yeah.
Because we might not have enough time.
Okay.
If you want, do you want to hear this cool proof?
This is A1.
Yeah.
Oh.
So I guess we found a nice way to write this. So basically, do you remember the question?
Yes.
So it's n to 9n, minimum number of leading digits, yeah? And the key is the proof, not the solving, I guess, especially for seniors. Okay, so we start with claim is 4, yeah? And then we introduce notation. So we say I is less than j if the leading digit's less, yeah? Okay, that'll save a lot of headaches. And maybe congruent if the leading digit's the same.
Yeah.
Okay, so it's clearly transitive. Okay, so then lemma 1. So this is the key lemma, even though it's like super obvious.
Oh.
Huh?
Oh yeah. No, I thought the assignment.
Yeah, it's the key to converting all the words into notation. So basically, all you have to do to prove that something has or one thing that suffices to show something has a lower leading digit is simply if you add 1 to the leading digit. So you start from n is like this, right? And the claim is if you add 10 to the k, you're increasing the leading digit as long as you don't carry over. Yeah. So yeah, I was saying that you could, in certain situations, you could probably just get away with saying this is obvious. And actually, if you don't say it's obvious, we haven't really found a good way to say it. But adding 10k literally adds the first digit by 1. Yeah.
Yes.
Yeah, but hopefully, like, this is the only really real writing in the whole thing, the notation and the first level. You know. So once you got that, you have sort of the next part of the proof is also like sort of the start of a lemma. So let L be the largest integer such that L doesn't increase the digits, yeah?
So it doesn't increase.
So n, 2n, all up to L and all have the same number of digits as n, yeah? Then the conclusion can be written nicely. The conclusion is this, yeah?
Attention, attention. This is a file evacuation system test.
Yeah, are you happy with lemma 1 now?
Yes.
Okay.
I had filled the notation and something.
Yeah. Okay. And the proof of the lemma 2 is pretty much just using lemma 1, right? So basically you have, for any I in there, I plus 1 is bigger than I plus 1n is bigger than in by n, right? And n is bigger than 10 to the k. So you've increased the digit by 1 without going over. No. And then the rest of the proof is just case batching L, yeah. So L could be greater than or equal to 4, it could be 3, 2, or 1. And if L is greater than or equal to 4, so the lemma already applies, yeah. Lemma 2 already says that these are all different. So you're done, yeah. So no more words, that's the kind of the key to this. So when L equals 3, yeah, you get this from the lemma 2. But the fourth one goes over, right?
Yes.
But instead of doing fractions and considering digits, you leave this expression whole, yeah? And you show that 6n is less than that.
Okay.
Yeah. And so that gives you that 10n is bigger than 6n plus 10k plus 1, you know?
Yeah.
Which means by lemma 1, 10n has a bigger leading digit than 6n, right?
Yeah.
Because 10n is less than 10 to the k plus 2. You know?
Okay.
And 10n has the same leading digit as n. So therefore, 6n is less than n, which is less than 2n. Or you could put 4n here as well, but it doesn't matter. Like after the lemma, the whole proof is wordless.
Oh.
So L equals 2. You start with this from lemma 1 or 2, yeah?
Yes.
And then the next one goes over. So you subtract that from 10n, and you get that 10n is bigger than 7n.
Yeah.
And if you do it again for 7n, you subtract 3, you get 4n. It's less than 7n. So then you get a chain of 4. And if L is 1, then 2n is bigger, right? And then 8, 6, 4, 2. Or you get a chain of 5 at least. Yeah. Yeah. Okay, so the third time, wait, that was the third time I said this.
Wow.
Because Yang arrived and then you arrived.
Oh.
But I think it was almost, 5-minute proof, see? After, yeah. I think it's good for some of you because it has no words basically past the. You could probably even get rid of the words in the first proof. It's just, it's hard to be bothered at the time, you know? Like adding, like if you really wanted to, you could write obvious, but that's like not really getting rid of the words. It's just kind of, yeah.
draw a picture and diagram.
Yeah. But in some sense, you put all the words into that one lemma, which is kind of realizing that 10 to the k is adding one digit. Yeah. All right. Is Crystal still here? Is there any questions? Where's Lucas?